Oops. Okay. All right. So welcome everyone. Thanks for coming. So we're glad to introduce Stevan Gajović from Max Planck Institute, who's going to speak on the probability that random p-adic polynomials have roots in QP. Please, Stevan.
Okay, thanks. Thanks for the introduction. Yes, and I have to start with saying that I'm sorry that this is online and I'm not in Brazil at the moment, but hopefully in the future I will visit Brazil. So today I will talk about the joint work with Bhargava, Cremona, and Fisher about probabilities of that random p-adic polynomials have roots in QP. Very soon it will be more precise. So it started actually by work of three of them on the density of hyperelliptic curves over Q that have points everywhere locally over Q. So it means that they have points over all completions of Q, QP, and R. Hyperelliptic curves are given by affine equation y squared equals to f of x. And the simplest case where we can claim that there is a point is when f has a 0. Of course, well, let's disregard the points at infinity. So this is a simpler version of this question. So when f has a point over, when f has zeros over QP, over QP for all QP, we don't look at real zeros now because they're very well investigated. So today we focus on p-adic completion. So today we show how to compute the probability that a random polynomial in ZP has a 0 in QP, or well, we restrict also for monic polynomials for a reason that will be evident soon. We compute the corresponding expectation and we extend to a fixed number of zeros. So we don't just compute the probability that it has a 0, that it has exactly 2 zeros or exactly 6 zeros or whatever we want. And we show that these functions are rational functions of P, so it doesn't depend on P. The result is uniform for all P, and there is some symmetry in P that I would like to point out. And as I said, since this is also semi-analytic number theory, maybe you care also about real polynomials. There are so many results about real polynomials, I will not talk about them now. So we are in p-adic world, which is nice. Unlike so in the real case, well, the measure of real numbers, the standard one, is infinite. Here we don't have this issue, so we can consider all ZP as the, well, it has hard measure such that the measure of ZP is 1. And since it's transitory invariant, well, this is just an overview. If we denote by dk the residues modulo P, so dk are just point elements of ZP congruent to K mod P, then all of these residue classes have the same measure, that's translation invariant, and all of them have a measure 1 over P because the whole space has dimension has a measure 1. And similarly, if we divide further by P to the M, all classes modulo P to the M have measure 1 divided by P to the M. We extend the measure from ZP to a power of ZP, so ZP to the N. Again, the measure of the full space is 1. And again, we want to, well, see some integrals today, I guess. So then today there will be p-adic integrals, but p-adic volume integrals, not p-adic integrals on curves. And so we can say that the measure of a subspace is just the integral over it. So when we start, if we pick a random number, what is a probability that's divisible by P? Well, 1 over P, we know that. So this way is actually to formalize the notion of probability. And we say that, so that the, instead of probability, we use the word density. So density of a subset is its measure inside of ZP to the N. And the probability of some event that is parameterized by coefficients in ZP to the N is actually the density of the corresponding subset which describes the event. Like here, if the what is the probability that a random p-adic integer is divisible by p? Well, it belongs to p(z)p, so it has measure 1 over p, so then the probability is 1 over p. That agrees with our intuition. And that's how we will compute these probabilities today. We also want to say that since we work with polynomials, we want to associate corresponding spaces to polynomials, and there are two important kind of polynomials. Well, all polynomials of degree at most n, then they just have index n, and if we add one up, then we restrict to the monic polynomials. And it's clear the first set corresponds to n+1 tuples of p-adic integers, and the second one corresponds to n tuples of integers because we fixed the coefficient 1 here. So that's how we will actually measure the probability. So if we consider, well, for simplicity, monic polynomials of degree n that have some property, then there is a set, that's a subset of zp to the n that corresponds to the set of all polynomials with that property, and we say that the probability of this property p is actually the measure of this subset as a subset of zp to the n. So it's important to keep measure of, to pay attention on dimensions, so that if we go into the space of dimension 1 less, then the measure is automatically 0 and so on. So that is the probability, and to warm up, well, the first goal will be to compute alpha n and beta n. So alpha n is what I said already before, the probability that a random monic polynomial of degree n has a root in QP. And when we restrict to monic polynomials, then having a root in QP is equivalent to having roots in ZP. And there is another probability that will be clear soon why we want to compute this. So that is the same probability, so that a random monic polynomial of degree n has a root in QP, but only restricted to polynomials that reduce to the x to the n mod p, like to the linear, the maximal linear power, so nth power of a linear polynomial mod p. Are there any questions so far before we go to one example? So let's start, well, first to see alpha 2, so degree 2, consider a monic quadratic polynomial, and we consider its reduction. So then f bar, so bar is today the notion of a reduction, and so f bar is a quadratic polynomial over fp. There are only finitely many of them, and since we consider monic polynomials, so there are only p squared monic quadratic polynomials over fp squared. And it can happen, well, three situations can happen. The first one is that the quadratic polynomial splits into two linear factors. So then f bar has a root modulo p, that's a single root. By Hensel's lemma, any of two roots can lift to a root of the starting polynomial in ZP. So that's easy. The second case, if f bar is irreducible, so since it's irreducible, well, it implies that f bar also has no zeros in fp. So the starting polynomial f cannot have any zeros because they would reduce to some zeros modulo p. So these two cases are easy. And now we see why we need this beta n probability. So there is the third case when f bar is a square, so a square of a linear polynomial. In this case, we have to do something extra to see what is going on. But this is precisely beta 2. So this is a monic polynomial whose reduction is a square of a linear polynomial. You shouldn't be confused with x squared and x minus a squared, because they are related by a linear change of variables. And as we know, linear change of variables prevents the measure. So then we can assume that a is 0 without losing the generality. And then, so we have an equation for alpha 2. This is, we have a sum of 3 elements. So the first element in the sum corresponds to the first case. So the probability is 1. And this is simple combinatorics. So we have to pick 2 elements in FP. This is P over 2. And the probability of this case, as I said, there are only p squared monic quadratic polynomials over fp. So everything has to be divided by p squared to get the corresponding probability. If f is irreducible, then it generates elements of fp squared that are not in fp. So there are p squared elements in fp squared minus p elements that are in fp, and divided by 2 because they all can come in pairs. So that is the second case. And the third case, there are only p linear polynomials over fp, so p squares of linear polynomials. So this is, I hope, simple and clear, but this is all we need for alpha 2, well, except that in higher degrees it will be more complicated, but the principle is important. So as we will see soon. So then to finish this example, as I said, we can assume that actually the reduction of f mod p is just x squared. So then we can assume that coefficients with x and well, the free coefficients are divisible by p. If this is a 0, we know that x is in x has to be a p-adical integral. So this is divisible by p, this is divisible by p, then x squared is divisible by p, hence x is divisible by p. So we can replace x by px to avoid making more notation. So we just replace x by px and divide by p. So here we will get p squared, here we'll get again p squared. So to be equal to 0. And here we already have a first conclusion. Oh no. Can you hear me? Yes. So if the a0 is not divisible by p, then, well, this equality cannot hold. So there are no solutions in this case. And this happens with the probability p minus 1 over p. That's what we know, because the other case, when a0 is divisible by p, so it happens with probability 1 over p. What happens when we replace a naught by p, a naught prime? Let's just divide p, and we get again a random quadratic polynomial monic. So the probability is again alpha 2. And then we see that we have a system of two equations with two unknowns that we can solve and get what alpha 2 and beta 2 are. And then we can really see that they are rational functions of p. So you might think of like this is a quadratic polynomial, maybe p equals 2 should be different. Well, we see now that it's not. So it's uniform for all p, we get the same result, and that will happen for all alpha n and beta n. And so this is simple principle how we compute these probabilities. Are there questions so far?
Can you just remind the definition of beta n in general?
Beta n is like here, that's a polynomial of degree n that reduces to x to the n. So here we have a quadratic polynomial that reduces to x squared. So in general, we have a polynomial of degree n that reduces just to the x to the n.
All right, good, thanks.
Okay, thanks. So then briefly, the strategy is the following. So what do? We divide all monic polynomials of degree n into three subsets. First ones are those that have a simple root. Well, so we divide actually their reductions. So if f bar has a simple root over fp, then by Hensel's lemma, f has at least one root in qp. That's easy. The other case is also easy. If f bar has no roots in fp, then f cannot have any roots in qp or zp. Well, don't forget that we are still in the monic case, so that's equivalent. And third case, which says that if f bar has roots over fp, but no simple roots, like we had a square of a linear polynomial. So it has roots, but no simple roots. Say that there are no roots. We cannot say that by Hensel's lemma we are sure that there are roots. So we have to do something more, and that's what we will see pretty soon what is going on in this case. So again, to repeat, So what is our strategy? We actually compute all possible factorizations or splitting types of polynomials f bar modulo p. So there are p to the n monic polynomials of degree n modulo p to the n. So we can compute the probability of factorization of each type, just how many of them divided by p to the n. Then in each factorization type, f bar, we need to compute what is the probability that f has a root in this case. So as I said first, in the case one, so if in the factorization there is a simple root, so we know that there is at least one root. In this case, probability is 1. In the second case, probability is 0. And then in the third case, we will get some other probabilities. And then just sum the products of the last two probabilities over all splitting types. And that is it. So that is the strategy. Consider all factorizations modulo p, then compute the probability of each factorization type. In each factorization type, see the probability that zeros lift, and then sum the two probabilities over, sum the products of two probabilities, and that's the answer. So first, as I said, we want to compute probabilities of each splitting type. So what is a splitting type? That shouldn't surprise you. So a splitting type of degree n is any tuple of numbers di, ei, whose sum dj or dj such as sum dj ej is equal to n, so that they can actually correspond to factorizations of some polynomials of degree n. We simply denote splitting types of degree n by Sn. And as I said, so a monic polynomial has a splitting type d1, e1, d2, e2 up to dt, et if it factors into irreducible components of degree dj to the power ej. So fj has degree dj and it's irreducible and it's raised to power ej. And then we say that the splitting type is d1 to e1 up to dt to et. And we denote it by sigma of f. And as an easy example, so if we have this factorization, then x squared, this is a linear, a linear polynomial squared, x plus 1 corresponds to 1. Well, when e1 is, when some ej is 1, we don't write it. We could put 1 here and 1 on 2, but that's not necessary. X squared plus 1, that's just quadratic, x cubed plus 2, so that's cubic polynomial raised to the power of 4. So that should be clear. And we want to compute probabilities. So we want to know the number of monic irreducible polynomials of any degree. So in this case, we assume that all of these polynomials here are irreducible. And there is a formula that induces the Möbius function, that uses Möbius function that to count the number of monic irreducible polynomials of degree n. And what will be important later, that when k is 1, mu of 1 is 1, p to the n plus lower degree terms. So it is a rational function of p, actually even polynomial in p, and the leading coefficient is 1 over n. Then we want to compute the number of monic polynomials in fp with the prescribed splitting type. Then it's clear that it is a polynomial function in the number of monic irreducible polynomials of degree 17. So it is also a rational function of p. I will not do the combinatorics here, but simply look at this example. So let's see how many there are polynomials of this splitting type. So we want one cubic polynomial that is raised to the power of 4, so that is n3. We want one quadratic polynomial, that's n2, and we want two linear polynomials that are not the same. They come with different powers, so we don't need to involve binomial coefficients. Then simply we just choose one on n1 way and the other one on n1 minus 1. So then you can see that for any splitting type, that's a simple combinatorics to compute n sigma, and this is indeed rational function of p. And what is then clear, the probability that a polynomial of degree n over fp has a splitting type sigma called lambda of sigma, is just the total number of them divided by p to the n, as I said, and this is a true rational function of p. Now, as a practice, so we want to do degree 3. So in degree 3, we consider cubic polynomials. So what can happen? Either the cubic polynomial is irreducible, or it has one linear and one quadratic factor, or it's a cube of a linear polynomial, or it's a square of a linear polynomial times another linear polynomial, or it's a product of 3 distinct linear polynomials. And sorry, this is not then lambda, this is n sigma here. So this is the number, total number of them. I didn't divide by, I forgot to divide by p to the 3. So then, as we can see again, it's some polynomial of p to see how many of them there are. And the probability of having a root is here easy. So if f bar is a cubic polynomial, so then f bar has no roots modulo p, then f cannot have roots in qp. In 3 cases, we have at least one linear factor. So we know that there is a 0, so this is probability 1. And there is the last case when when the reduction is a cube of a linear polynomial, and that's beta 3. So this beta n probabilities are really important. And here we divide it by p to the 3 and so on. So alpha 3 is just take the number of divide by p to the 3, multiply with the probability and sum them all. And I promise I will stop for the last one. I mean, here is the table. We don't need to go through all of them. You can convince again yourselves that, sorry, this is again n sigma I, not lambda. Lambda is divided by p to the 4. That this is indeed some polynomial in p. And again, when there are no components 1, so when there are no linear roots, then probability is 0. We have in 3 cases no, where there is no 1. When there are clear ones like sigma 2, sigma 6, sigma 8, sigma 10, sigma 11, we know there is a root, so the probability is 1. And we have our known case, sigma 7, when it's 4th power of a linear polynomial, that's beta 4 that we still need to compute. And there are 2 more interesting cases that we haven't seen before. So in sigma 5, we have a reduction that has a quadratic polynomial. So quadratic polynomial cannot have zeros. And we have a square of a linear polynomial. So then only this component can have zeros. So the probability in this case is actually beta 2, corresponding to a quadratic polynomial of degree 2 that reduces to quadratic polynomial that reduces to a square of a linear polynomial. And in sigma 9, we have 2 of them. So this is just the standard probability trick. The probability that the first component has no zeros is 1 minus beta 2. The second one also 1 minus beta 2. So the probability that there is no 0 at all is 1 minus beta 2 squared. And then we subtract 1 from this. And then again, we get the formula for alpha 4. We divide it by the total number of polynomials. This is n, sorry, and sigma I, pi. Important thing here, everything else is known. So we reduced degree 4 to smaller degrees. So we can compute 1 by 1. Everything is known except from beta 4. And we will see soon how to compute beta 4, similarly as beta 2, just with more steps. But before, so there is a warning. So what's in case 5 that I talked about, so the quadratic and the square of a linear polynomial, we have this thing. Can we assume that this square of a linear polynomial is random? Because we start with something of polynomial 4 of degree 4 and divide by something of degree 2. So we have to be careful to say that this is indeed beta 2. And even more in the case 9, when we have a product of 2 squares of linear polynomials, even if we can assume that both of them are random, can we prove that actually that events of lifting roots, having roots that lift A and that lift B are independent? So we have to check this, we have to prove this, which we won't do, but I will give the steps for this. And so it is important here to see, well, that we just use polynomial Hensel's lemma. So polynomial Hensel's lemma says if a polynomial with p-adic integral coefficients factors into two factors that are co-prime, so g bar and h bar are co-prime, and g is monic, g bar is monic. So then we can lift even factorization, not just that we lift zeros, we can lift factorization. So if f bar is a product of g bar h bar, then there are polynomials in ZP, G and H, so that f is actually the product of G and H, and that G reduces to G bar and H reduces to H bar, and we keep the monic assumption so that we don't increase the degree of G. It can happen that one of two polynomials have higher degree, but not both. For one, it's fixed, and that's what we assure with the monicity assumption. So then all factorizations possible up in p-adic world corresponding to the factorizations in the FP world. So what this lemma assures that we can actually assume that all possible combinations here in, for example, case 9 will appear for G and H. Because if we start with two polynomials that reduce, then that's okay, but we want the other direction. So if we start from the product of two polynomials over FP, can we lift to anything? Yes, we can. So that's in principle how we use this Hensel's lemma to prove that the answers on both questions are yes, so that this table is indeed correct, and then we can compute alpha 4 in the described way. And finally, the promised beta 4. So again, we can assume that f bar in this case is just x to the 4. And now watch carefully. Here everything is easy, and this is the main principle. So all coefficients except from the leading one are divisible by p. So x has to be divisible by p. Replace x by p, x divide by p. Again, we get everything divisible by p besides a naught. So if p doesn't divide a naught, there are no zeros. Otherwise, with the probability 1 over p, a naught is p times a naught prime. We just replace a naught by p, a naught prime, and divide by p. And keep track of so this is the highest power of p to the p cubed, how this will decrease. So now it is p squared, p, and unknown coefficients. Here we can use Hensel's lemma again. If it doesn't divide a1, so then the reduction of this polynomial is a linear polynomial that has 0. Linear polynomials always have zeros. So in this case, there is a 0 certainly. Otherwise, if a1 is divisible by p, then we are in the same situation as we started with. All four coefficients, well, the first four coefficients are divisible by p, and the last one we don't know what to do. So we again make two cases. If p now doesn't divide a naught prime, again there is no 0. If p divides a naught prime, then replace a naught prime with p a naught second, and put p here and delete 1p. And here is this rule. So we started with p cubed. Everything else was divisible by p. After first change, it decreased to p squared. And now a linear coefficient is not anymore certainly divisible by p. And after new transformations, p squared decreased to p. And now we have to argue what a2, if a2 is divisible by p or not, then if a1 prime is divisible by naught or a naught second. So this principle can work for any n. Just with more steps. So if is not divisible, if it doesn't divide A2, then again by polynomial Hensel's lemma, the probability in this case is actually alpha 2, because it reduces to a monic or, well, some coefficient to a quadratic polynomial over Fp. So if it divides A2, then we are in the situation like this one. So again, if P doesn't divide A1, yes. If otherwise, we again argue the last coefficient. If this one is not divisible by P, no. If yes, then we put P here and discard all P's. So we get again some random polynomial of degree 4, so probability alpha 4. As in our beta 2, we had probability alpha 2. Here, again, we have another equation that beta 2 is actually something known plus something times alpha 4. So we can actually solve and compute beta 4 and alpha 4. And this works for any n. So I hope that we now see that it works for any and both formulas. So I just gave them as for 4 because I thought maybe it would be easier to see concrete examples. Everything works the same, except that, well, we have some maybe indices or to pay more attention. And as we can see, alpha n and beta n are truly rational functions of P, so they don't depend on P. Now, if we remember the title, we didn't use the monicity assumption in the title. So we want to compute the probabilities of a random polynomials of degree n having a root in QP. First of all, we first make one restriction. We just disregard polynomials that are not primitive. These are polynomials that have all coefficients divisible by P. So we can only consider primitive polynomials. That's a simple calculation. So we don't look at polynomials with all coefficients divisible by P. So then F bar is some polynomial that has degree, and degree of F bar is called the reduced degree. And it's again a quick combinatorics to compute the density of the primitive polynomials of reduced degree M that I will skip. So that this just means that all coefficients higher than M are divisible by P. And that the coefficient with M is not divisible by P. Then, as I said, as a Hensel, now we use polynomial Hensel's lemma with factorization, where the second factor is 1. And 1 is coprime to everything. So then we actually factor F into a monic polynomial of degree M. This is G, and a polynomial H whose reduction is 1. And then the roots of the polynomial F have to be roots either of G or H. If they are roots of G, then we know that's probability alpha M, because that's how we defined alpha M. The tricky one is H, because this has reduction 1, so it cannot have zeros in ZP. If it has zeros, it actually has zeros in QP, but not in ZP. And here, well, we don't assume that the polynomial is monic, so it can have zeros in QP. And what do we do? So we have a polynomial with all coefficients except from the from the last one divisible by P. Well, let's reverse it. So let's start with the polynomial whose first coefficient is not divisible by P and all others are. Then zeros of both polynomials are, well, in 1-1 correspondence, x to 1 over x, because actually 0 is not a 0 of any of two polynomials. And then the reverse polynomial, here denoted by h prime, has reduction x to the n minus m. And we see that is our beta probability. So that's how we compute the probability in the general case. So we restrict to polynomials of reduced degree I. Then either the monic polynomial has a zero with degree with probability alpha I, or the other polynomial has a 0 with the probability beta n minus I. And again, we use the trick of having no zeros to have this expression. So this is just for having zeros in QP. Are there any questions so far? If not, then oh no, what is it? Ah, okay. So this is for having at least one root. Now, as I said, what if we want to compute the probability that polynomial has exactly two roots? And we use the same notation, I mean, accordingly, the same notation. So just for random degree n polynomials, the probability of having exactly r roots is rho star of nr. So the first one is degree, the second one is our wish for the number of roots. If we restrict to monic polynomials, then it's alpha star. If we restrict further that f bar is x to the n, that we denote by beta star. And then, well, simply to recall the expectation. So we have the number of roots, we have the probability, then the expected number is just their product. So the product of r times rho star n r is the expected number of QP roots of a random polynomial of degree n that we will show how to compute soon. And now we want to actually expand this. What if we don't want just to consider roots, but we want to consider unordered pairs of roots, distinct roots, or just this is just a set of two elements, just a set of two distinct QP roots. So what happens in this case? If f has zero roots, then there are zero sets of size 2 of roots. If there is only one root of a polynomial, then again there is zero sets of size 2 of roots. And then things gets to be more exciting. If there are exactly two roots of f, then there is exactly one set containing both of them. If there are three roots, then there are three sets as 3/2 binomial coefficients, and so on and so on. And here it's important to see that the probability of having exactly two sets of 2 is not possible, because 2 is not n/2 for any n. And then the expected number is again just the sum of probabilities times the number of 2 sets. So that's what is the next. The expected number of sets of size d, that we shortly call d sets, of a random polynomial of degree n, we denote just by rho n d. So here d denotes the size of a set that we want. And again, if we restrict to monic, that's alpha. If we restrict further that f has a reduction x to the n, then it's beta. So I hope with these tables that this is clear. And the first formula should be indeed clear. So the expected number of d sets of roots of a polynomial of degree n is precisely r/d. So then in the case when with the sum of all r/d, when there are exactly r roots. When there are exactly r roots, then there are r/d sets of size d. And there is an inversion formula. So that's what we can claim. If we compute all numbers of one kind, we can compute all numbers of the second kind. So if we know all rho n's, we know all rho stars. If we know all rho stars, the other way. If we know all rho stars, we know all rows. If we know all rows, we know all rho stars. And here, as you can agree, a rho can be replaced by alpha or beta. Everything works the same. This is just combinatorics. So this is the notation we will use. And quickly, so this is also this was investigated just for the number of roots, and it was in many papers. So I quote what was done before us, and that they proved that the expected number of roots of a p-adic random polynomial of any degree is 1. That is interesting. Also, what was done before, Buller, Gonstein, Moser, Rosenberg computed the probability that a random p-adic polynomial splits. So having n here means that all n roots are in QP, so then the polynomial splits into linear factors. So that was computed before. And what is also interesting to note, the probability that polynomial of degree n has exactly n-1 root is 0. I mean that it has to have some double root, so that happens with probability 0. And what we computed, so we computed alpha star of 2 is alpha 2. So a polynomial of degree 2 can have 0, 1 or 2 roots. As we said, it can have one root with probability 0, so we disregard. So if it has roots, it has 2 roots. So alpha star 2 is exactly alpha 2, and beta star 2 is exactly beta 2, and similarly for rho. This is what we computed. So we now compute the probability of having no roots for alpha beta, and from the formula for rho, we can compute that rho 2 is 2. So rho star 2 is 2, and rho star on 2 0 is 1/2. So a random quadratic polynomial in QP has a root with a probability 1/2. That's interesting. Okay, now I think we all know what the resultant is. Just to recall, that's the product of all differences of roots of two polynomials times some number that corresponds to the leading coefficients and degrees. Yeah, so this is analytic seminar, and then I wanted to put some more interesting stuff for you. So the first thing is that the multiplication map viewed as map on coefficients of polynomials has Jacobian given by the resultant. That's an interesting thing. And we will see soon the second interesting thing. So the resultant tells us if polynomials have the same root. If this is 0, then they have the same root. And so if the resultant is a unit, it means that if they don't have polynomials, then the polynomials don't have common roots modulo p, so f bar and g bar are co-prime. But we have, well, there is one condition. We also need to take care about this coefficient that comes into resultant. So we actually have to have that at least one of the leading coefficients of f and g is a unit. But this is some lemma that we use in the following lemmas. So I wanted to show you this lemma because of the sketch of the proof. So what it says, if we have a set of monic polynomials of degree m and a set of polynomials of degree at most n, or monic polynomials of degree n, so we have two cases, doesn't matter for the proof, then and we have their their product has to believe in the polynomials of degree n plus 1, either monic or at most n plus 1. If by chance the multiplication is a bijection, and if the resultant of all polynomials of A and all polynomials of B is always a p-adic unit, then this bijection is measure preserving. So that is what we want, because we want the probabilities that these are actually measures of some sets. And this is why I wanted to show. So as we said in the integral, when we change the variables, we have to have the Jacobian factor, and Jacobian factor is, as we said, the resultant. And the assumption here is that the resultant is a p-adic unit, so we can just disregard. And here is the measure of the AB, and here is the measure of A times B. So that is quick, and I hope you like it. Sorry, I think this is the last ugly notation that I have to introduce today. So what do we have here? If we start with a monic polynomial of degree n, then by pf over fp, by pf we denote all polynomials of the same degree that reduce to this polynomial. So for x squared plus 2, we have monic polynomials that reduce to x squared plus 2. So this coefficient is divisible by p, and this coefficient is congruent to 2 mod p. And this is not sufficient for our purposes. We also want to allow polynomials of higher degree. So if we want, we can have polynomials of degree 4 that reduce to x squared plus 2. So then, of course, the coefficients with x squared and with x cubed and x to the 4 has to be divisible by p because it vanishes there. Then we have non-divisible coefficient by p with x squared, so 1 plus pc. And again, the rest is the same as before. And the third one is just the set of polynomials. BMN denotes the set of polynomials of degree at most n, whose reduction has degree m. And for here, B24 is just, well, the first two coefficients are divisible by p. That's it. BMN just means that all coefficients higher than m are divisible by p. Oh, yeah, that's... and here, yes, we have this assumption that it's monic. So we have this coefficient is 1 plus p times something. And here are the key lemmas for our independence results. So I will not go into, well, the probability theory. So I will just say, if G and H are polynomial in Fp that are monic and co-prime, then the multiplication map Pg times Ph to Pgh is a measure preserving bijection. And that is exactly the case that we had, for example, in genus in degree 4. So this lemma assures us that we can compute the number of roots of a polynomial f that is a product of two polynomials that reduce to G and H as the sum of the products of the sum of roots of polynomials themselves, both of them. So this is the key lemma. And the second one is just the case that I commented when we consider general polynomials. So general polynomials, unlike monic ones, can have leading coefficient divisible by p, and we still want to have the same result. So this is the second thing. So this is lemma 2 corresponds to this, to this formula. So from lemma 2, we obtained, we proved that this formula is correct. And from lemma 1, for example, we have this this statement, yes. So from lemma 1, we can count the number of roots as the number of roots of its factors, the sum of number of roots of its factors, and the same for the other one. So that is the point of these lemmas. And the proof is then straightforward. By Hensel's lemma, we proved that this is a bijection, and then by previous lemma, we proved that it's measure preserving. And now we are ready to state the formulas between alphas, betas, and rhos. So for a splitting type of degree n sigma, we denote by alpha the expected number of these sets of a monic polynomial of degree n whose mod pli splitting type is sigma. That's what we did. So we considered all splitting types, and in each one of them, we computed probability. Here, well, we do the same just for the expected number, so that the actual expected number is the sum over all splitting types times the of, well, p minus to the n. So that's the probability. For the probability, there are exactly n sigma of them, and the probability in this case. So this is no surprise. This is the same as we had before. And as we say, so then we relate alphas and betas. So this special case, so when polynomial mod p has splitting type which has exactly k powers of 1, then the only this part can contribute the roots. So all higher numbers correspond to reducible factors. We can disregard them. And the case 1 to n1, for example, corresponds to a polynomial of degree n1 whose reduction is x to the n. So this is actually beta n1. And so on, the last one corresponds to beta nk. And we want d roots, and we have k factors. So if the first one comes with d1, the second with d2, the last with dk, their sum has to be d. And we have to sum over all possible sums of d as a sum of k non-negative positive numbers, and to multiply the probabilities by previous independence lemma, we can use this product. So this is the relation between alpha and beta. Between beta and alpha, we saw it's the same. So either we by probability p minus 1 over p, we conclude something, or by probability 1 over p, we go on and go on. So this is a general shape of the formula that we solve for beta 4. And again, for rho, we again deduce this by looking at the reduced degree p to the m. And in the case p to the m, so it has a monic factor of degree m, and some factor whose reverse polynomial is a factor is a polynomial that reduces to x to the n minus m. And again, if we want d roots, then if d1 come from alpha from the monic, and d2 come from the second factor, then d1 plus d2 has to be d. So these are the formulas that relate them. Are there any questions? I mean, if there are questions, maybe better now, because this is the main thing. Now I will just show some formulas and that's it. If not, what was nice that we could manage to put all of these three formulas into nice relations between the following generating functions, a, b, and r. So then I will just show them. I mean, we won't waste time on them. And then from these formulas, we can actually compute, and from the previous results, we can actually prove that alpha, beta, and n are indeed rational functions of p. Well, we saw this, they are a solution to some system of rational functions in p. And we have the symmetry that rho of p is the same as rho 1 over p. And when we replace p by 1 over p, we go from alpha to beta. That is interesting. And that we can prove if we replace p by 1 over p, well, the generating functions will change their roles. So that's how we can prove this. So this is...
So what does rho of nd of p mean?
What?
The two last lines.
A rho of nd is the some rational function of p.
Okay.
We just plug in p,
all right,
and we just plug in 1 over p, we get the same number.
Okay, but I mean, but the left hand side means that you're looking at fp, and the right hand side, I mean, it's not.
No. Rho of nd is just a function at p. You can plug in
also,
p.
It was defined initially as you count in probabilities, right?
Yes, well, expected number, but yes.
Okay, sure, but let me, all right, sorry. Go.
Yes, well, okay, then, like here, for example, you always get some functions of p, and then when you replace p by 1 over p, you go from here to here, and here it stays the same. So you can see on this example, 1/2 that's okay, clear. But in general, that can be proven. Yeah, where is this? Yes, so that's it. Okay, then I will, yes, sorry, then this was a bit, I should finish soon. So we can actually prove further that alpha, beta, and rho stabilize when n is sufficiently large, then all of these quantities are the same. Because if this is a polynomial, then terms have to cancel each other. So alpha is stable, beta is stable, rho is stable. Then I will skip this. There are corresponding generating functions just if we consider polynomials, the density of polynomials with a root. And there are interesting results about asymptotic results. So as we saw, these are rational functions of p. So we can wonder what happens if p goes to infinity, because we can actually see that in alpha and alpha star, the numerator and denominator have the same degree in p. And but yeah, maybe I can stop. Sorry, yes, that it was a bit. Yeah, that's it. And if there are more questions, I will talk.
You stop it?
Yes.
You don't have a thank you slide at the end?
Yes, I do, but I stopped before this.
Oh, so you finished the talk or?
Yes, yes. I mean, it's
Okay,
55 minutes, so I have to
that's
stop.
great. So let's thank you. So let's open for questions then. So I have one which is I think I remember from last time I've seen you talk. So you were, was there a specific reason for looking at these probabilities, some kind of application in mind or?
Yeah, well, that was the first slide that the.
Oh, that's when you were going super fast.
So then that's just a probability that a random hyperelliptic curve has an affine Weierstrass point.
I see.
Yeah, that was one. Well, that's how it started. But there are, I mean, over real polynomials, there are many results with different distributions of coefficients. And this question was of interest of them, yes. And well, there is this probabilistic p-adic Galois theory that people also research. So this is, you know, baby version maybe of this.
I see.
So there are other questions related to.
Okay. And is so the fact that the all right. Okay, no, never mind. I answered my question.
Any more questions? Yes, I see.
Kevin, ask a question?
Oh yeah, I have a question, but there's one in the chat if you wanted to address it first.
Oh, okay, I didn't.
But then I have a question after that, if that's okay.
Yes, there are papers about, for example, zeros of eigenvalues of matrices over ZP. I'm not very familiar with that, but there are results on the characteristic polynomials of matrices and distribution of having how many zeros. So that's what I know about it, and I know that you can look at Antonio Larario's website. He has some paper about it. I don't know the title precisely. So it's in CISA Trieste. So that I hope that answers. Okay, thanks. Yeah.
Okay, so my question may be very dumb, but when I see that you have a rational function in terms of p, and then it has this nice symmetry property replacing p by 1 over p, that reminds me a lot of the Weil conjectures, or I guess really Artin conjectures, which, and like with the Riemann hypothesis over finite fields or for function fields. Is there anything like that here? Any sort of version of?
Oh no, that's
eigenvalues have
or uses zeta functions, but it wasn't helpful in this. Yeah, that didn't work. I mean, the proof is just combinatorial. There are recent results in more generality. Yeah, but it's not. I mean, it was a way first to try it, but well, the straightforward ways didn't work this way.
Okay, thanks.
Yeah, sorry, I didn't have time to go. Well, there is even one appearance of log that I wanted to show, but maybe.
That's you trying to please the crowd?
Yes.
I see. So you said that there are results on the real case, and do they look the same somehow? I mean, can you see some like?
Oh no, well the real polynomials and p-adic polynomials are quite different. I mean, for real polynomials, yes, you have more analysis, and
not the proofs, but the result. So, for example, so what you can do is like you take a monic degree 2 polynomial, and like coefficients are bounded by x, and then you. Okay, no, I'm not sure. This is a good question.
I think
yes,
there's
well,
also
that's
disparity for real.
Sorry?
they
polynomials.
looked at many. I mean, even just coefficients with -1, 1, or between -1 and 1, or there are
But you also
different
worry as soon as you have like
probabilities and distributions
So, okay.
between formulas there and here. I don't expect them.
Yeah, the problems were quite different. Too. Oh. Yeah, that's true. That's true. I guess. I think Hansel's lemma really makes the game completely different. Right?
Yes, here really it's nothing beyond Hansel's lemma. I mean, and manipulation with expressions and integrals.
Yeah. All right.
Oh, yes, of course. About real polynomials, yes, it makes sense to consider only even degree polynomials, or to count the number of zeros, because it has at least one.
Right.
Oh yes, RT, yes, I think so. Yes, we haven't tried. But yes.
Right. Well, thank you again.
Thank you.
So, are you in the small room, second floor in Max Planck?
No, I'm in Groningen. I was working with my supervisor, and then I, by accident, saw your message, and I said, okay, first I'll find some room quickly.
Okay. Thanks for that. Yeah. So the time was correct until the time change, and then we were trying to be smart. But I mean, it's best thing is just to say Brazil time, and then the audience tries their best to find out how.
Yeah, well, that's I saw that. I mean, in the website it says Brazilian time 13, and it said 13 as well. Then I assumed there were no changes,
Yeah.
but I didn't count that. This time
Yeah.
is different.
It happened the same problem last time so it happened last week because in the text before the little cards with your face in the text it was also written the same thing. So the speaker got it wrong, and then we corrected on the text, but then on the cards it's still wrong.
Oh.
And in the email we always say, yeah, whatever. I mean, hopefully this time I think we spotted all the points of I could go wrong.
Yes, or maybe you should tell the others to.
Oh.